Thanks a lot for inviting me. I'm happy to speak. Yes, so this is joint work with Gil Cohen, Oris Berlo, and Amnon Tashma, all from Tel Aviv University. Do you hear me okay, by the way? Mm-hmm. Okay. So if you have any questions, please scream at the screen or something, because I can't see you. So hopefully I'll hear you. But yeah, feel free to stop me anytime and ask questions. I'll try to go slowly, but in case there are any questions whatsoever, feel free to stop me. Okay, good. So let's begin. So what's our problem? A very natural one. So we're given A1 up to AN, W by W matrices, and we want to compute, or today we want to approximate the product A1 up to AN. So yeah, it's obviously one of the most fundamental primitives, even just for the matrix powering case, where all AIs are the same. But beyond the algorithmic implications, it's also a very important problem in complexity. Because indeed, we now know that we can get better understanding of space-bounded computation through the lens of some canonical linear algebraic problems. For example, IMM and other problems. And what we will be interested in the space complexity of approximating the product, or even matrix powering, or even A to the N. Okay, so we have A1 up to AN. Each AI is of dimension W. Okay, so this is what we'll be interested in, and I'll try to motivate why. But first, let's set the ground and define the model of space-bounded computation. So it's a standard model of a probabilistic space-bounded computation in which we have an input tape. But for those of you who are unfamiliar with this model, note that we cannot replace the input with intermediate computation. It's just a read-only input. We have our work tape in which we do all our auxiliary computations, and we can use random coins. We can toss random coins, but know that if we want to save them and to look back at them, we need to save them in our work tape. So the random coins tape is read-only. Okay, and of course, we have our output tape in case we want to compute a function, or just to accept or reject in case we want to decide a language. And the quantity we're after is the space complexity, which is just the number of cells we used on the work tape. So if we're talking about languages, we say that a language is in BP space F. If there is a Turing machine, a randomized one that accepts it using space O of F of N with two-sided error, say with error 1/3. And we defined our class BPL, the class we're interested in, is just BP space of log n. Okay, what can we do with just very small amount of work tape, of auxiliary memory? Okay. And in this kind of research, what we would really want to do is eliminate, but of course, we don't need to either accept or reject. We can also, of course, compute a function. For example, IMM. It's a function and we output it on the output tape space efficiently. Okay. So our goal is to remove the need for random coins. And this is the corresponding deterministic space-bounded class, which we call D space F of N. In case F is log N, we just call it L. Okay. Good. Is it okay?
Yes.
All right, cool. So indeed, the BPL versus L problem asks, can we de-randomize any space-bounded algorithm with small space overhead? So can we take a space S randomized algorithm and turn it into a space S prime, deterministic one, hopefully where S prime is only O of S. It actually suffices to study the small memory regime, the log n space complexity. And the question is whether BPL is equal to L. And if you believe circuit lower bounds, quite plausible circuit lower bounds actually, BPL is equal L. So we believe that the BPL is equal to L. It follows from circuit lower bounds. But unlike the time-bounded regime, the BPP versus P problem, here we do have explicit results, which I'll mention right now, actually. Okay. So we had significant progress, as I said, getting explicit results. So what do we know? So RL, which is the one-sided error version of BPL, is already in D space log squared n, which I'll just call L square. This just follows from Savage. And it's not hard to extend Savage and prove that BPL is in L squared. Okay, so the seminal Nissan's PRG from the 90s give us a way to de-randomize BPL simultaneously in space log squared n and polynomial time, which the previous result, it doesn't follow from the previous result. A few years later, cleverly building on Nissan's work, Saks and Zhou proved that BPL is in L to the 3/2. And both these results I'll heavily rely on in this talk, but you don't need to know them in advance. I'll cover what's needed. Recently, using new machinery from what we call the low error regime, William Hosa managed to shave off square root log n factor. So we now know that BPL is in L to the 3/2, the minus little o of 1. So we already broke the 3/2 barrier. And there were other important milestones. For example, Nissan and Zuckerman considered the case where you want to de-randomize algorithms that toss very few coins. So for example, if you know your algorithm only tosses polylog n random coins, you can fully de-randomize it. Impagliazzo, Nissan, and Vigdorsson gave PRG with the similar parameters to Nissan, which turned out to be very versatile and important in future works that considered some other models. And also, of course, Reingold's famous undirected ST connectivity in log space, you can also view it as a de-randomization result. And we also have nearly optimal results for more restricted classes of computation, for example, some subclasses of branching programs and other computation models. Yeah. Okay, and if you're interested, William has a great survey. I think it's called Recent Advances in Space-Bounded De-randomization, I think. So yeah, if you're interested, it's a great manuscript. Okay, now let's switch back to the problem of IMM, and then later we'll see how they both connect. So what about approximating IMM, sorry, of course, computing IMM exactly, not approximating, but computing. What can you say? So you can do repeated squaring and do that in space log n times log n w. So when n and w are polynomially related, this means that this problem is in L squared. Now I'll mention like a nice fact, which I'm not sure it's so well known, that you can actually get log squared w plus log n, which is better when n is very large, using a Cayley-Hamilton-based algorithm, not a repeated squaring-based algorithm. But it only works when all the AIs are the same. It's just a nice fact to know. It's an easy algorithm. I can give it to you offline if you want. Okay, but this is computing exactly. What about approximation? Can we do better? So the game is essentially between the optimal L and L squared. This is our game. But if you want to be, for those of you who are want to be a little bit more precise, it's actually between L and the class called det, or which is subclass of NC2, which is subclass of L squared. So we know how to put it in det, but roughly the game is between L and L squared. And for general operators, for general real matrices, nothing better is known than just repeated squaring. And the question is, okay, let's try restricting our operators. And it's I think it's a fabulous fact that doing approximate linear algebra tells us a lot about space-bounded computation in the different models. So for example, if you want to approximate linear algebra for symmetric operators, this is often captured by the class BQL, which is the quantum analog of PPL, which I will not talk about today. If you want to do approximate linear algebra on stochastic operators, this is roughly captured by PPL, the class which we will be interested in today. And if you want to do doubly stochastic operators, a recent line of research tells us that it's already in almost L. So it's like log n times log n. Okay. Great. And our focus today is on arbitrary stochastic matrices. So why is it important? Even just matrix powering, when n and w are related, it's already complete for BPL. In what sense? On one hand, we can convert any probabilistic space-bounded Turing machine into some stochastic operator A, such that the probability to move from any state S to T is just the matrix powering A to the n in ST. That's easy if you kind of have some familiarity with the model. And on the other hand, we can approximate random walks by just estimating the probability by taking multiple random walks, okay, and the corresponding Markov chain. So essentially, the randomizing BPL in OFS space is like approximating matrix powering deterministically in space OFS. Okay, this is one of the reasons it's very interesting to study. Okay, so what's known? Again, we want to approximate IMM for stochastic operators, and we want to distinguish between n, the number of matrices, and w, the dimension of each matrix. So if you do iterated powering and you truncate whenever necessary, you can do roughly log n log w. Nissan's generator and also INW gives us log n times log n w, but actually in a more black box manner, which I will mention soon. So it gives a specific algorithm, which we can actually utilize its very specific and nice properties to improve on things. I'll show it in a bit. Saks and Zhou gives us log to the 3fn, which is the term that dominates when n is roughly w. But in general, if you want to distinguish between n and w, this is log n to the power of 3/2 plus square root log n times log w. Okay. And sorry, when all AIs are the same, and we want to distinguish between n and w, what is the corresponding de-randomization problem? It's de-randomizing two-sided L algorithms that use log w space and n bits of randomness. Okay, this is how we should correspond w and n to the space and number of random bits of the algorithm. Okay, does make sense? Okay. So what's our result? We solve IMM in space nearly log n plus square root log n log w. So we managed to shave this 3⁵ power, okay, from the first term. And when w is not so large, let's call it the medium w regime, or looking at it from the other direction, when you have many matrices compared to the dimension of each matrix, we can get the nearly optimal O tilde log n. Okay. And just in the lens of de-randomization, if we consider a randomized algorithm that uses space S and tosses R random coins, the general setting is when R is 2 to the S, right? We're allowed for the algorithm to run into 2 to the S time, and it can toss 2 to the S coins. The Nielsen-Zuckerman result tells us that for R, which is poly S, we can simulate the algorithm deterministically in space 2 of S. That's what I mentioned, the result that talks about tossing few coins. Our result is the other extreme, where the algorithm tosses many coins, like 2 to the S to the C for some C greater than 1. And if you want to compare ours to Saks and Zhou, we get space S to the C over 2 plus 1 versus S to the 3C over 2. Okay, so this is the randomization result. So just to recap before moving on to the techniques, what do we have in our landscape? So if W is, say, constant or very, very small, actually IMM approximation is almost trivial. You can do it with nearly log n space. So there, the question is actually a black box challenge of constructing a PRG. And I'll mention it towards the end of my lecture. But right now, just know that the constant W is not an algorithmic challenge, it's a pseudo-randomness challenge. For the medium W, let's say 2 to the square root log n, or this regime, this is our result. When W and n are polynomially related, we have the Saks-Zhou result and we have Pose's result. And the extreme large W is the Nielsen-Zuckerman result, which I mentioned a couple of slides ago. Okay, so I'm going to move on and talk about the actual algorithm and the components that we're using. So if there are any questions about the result themselves, let me know. Okay. Okay. So we use let's say, 3 components. 2 of them are from the 90s. Maybe the third one is also from the 90s, but let's wait till we get there. So we have 2 classical results. The first one is Nissan's generator, but I'm going to view it not as a PRG, but as a randomized matrix powering algorithm. And I'll soon elaborate on it quite a bit. And we're going to use Saks and Zhou's framework, which uses Nissan's generator together with a shift and truncate mechanism in order to recycle randomness. Okay, but you don't need to know any of this because I'll define them later on. And the third one is more recent in the space-bounded community. It's the preconditioned Richardson iteration, which is just gradient descent essentially, and it's used as an iterative method for solving linear systems in optimization works, in time-bounded works, but it has recently appeared in space-bounded works and already found many applications. And there we use it also in today's work. We use it as a way to obtain high precision approximation of matrix powers and matrix inverses from mild approximations. Okay, so to kind of get started with the algorithm, let's start, and actually this will be most of our talk. Let's start with the case where all AIs are the same, because it already has many challenges. I mean, yeah, I guess the main challenge already appears here. Okay. Okay, so Nissan generator, as I said, we can view it as a randomized matrix powering algorithm, which is a very space efficient one, but it needs kind of a lot of random bits in the sense that those random bits are what we call offline randomness. We need repeated access to them. We cannot just toss them and forget about them. We need repeated access to them. So in terms of parameters, what's Nissan's algorithm, the way we will view it today? It gets the matrix, some seed or some string or some randomness string h and n, and it approximates a to the n. Epsilon will be our accuracy parameter, and delta, we call it a confidence parameter. It tells us that with probability at least 1 minus delta over the h's, if we apply Nissan with this h, with this good h, you'll get an epsilon approximation of a to the n. And the two quantities to keep in mind is the space, which is good. It's like logarithmic in the parameters we want. But the length of h, you should think about it as like log squared. And S is the number of bits we represent the matrix in. So it's like S times log n plus log squared n, at least. Okay? So what do Saks and Zhou tell us? Let's try, to raise a to the power of r, and r is 2 to the square root log n, for square root log n times. So a to the r, and then to the r, and then to the r, etc. Square root log n times. This will give you a to the n. Okay. And of course, the question is, okay, you apply Nissan repeatedly, but with which h's? In which seed do you use? So of course you can do independent HIs, but I mean, you're better yet just applying Nissan with to approximate a to the n. I mean, it makes no sense. It's too costly. What about staying the same age across all iterations? Now, a priori, it doesn't need to work. And it's not like a union-bound issue. It's an adaptivity issue. So suppose H, there are many H's which are good for A, but once you computed Nissan AH, your result depends on H. So it's seemingly possible that future iterations will fail miserably. Okay, we have an adaptivity issue here. But you should keep in mind that a good AH, like a good output of Nissan, should not heavily depend on H. Because if you're good, you're actually close to a fixed value, right? Which does not depend on your internal randomness. And the question is, how can we, I mean, there is, of course, there can be some dependencies, and how can we get rid of them? And the cool mechanism, which is now used in many other works, is the shift and truncate. So it's a very general paradigm, and it makes a lot of sense. So bear with me. Let's discuss it more generally. So you have an algorithm that takes an input x and some randomness y, and it approximates some value f of x to within high accuracy. Let's call it epsilon. And let's say f of x is, as you see, 1.5123. Now you can run the algorithm for like a couple of randomness strings and get like two good invocations. One gives you, okay, so you see here, one with y1 and y with y2. So both of these results are good, but they also depend on the internal randomness. So given the output, I might learn something on y. But what happens here if I take my value and truncate it to a higher error, say epsilon prime? Say epsilon prime corresponds to truncating after 2 digits. What happens now? Same value, right? We obfuscated the dependence on the seed. But is it always the case that after we truncate, we no longer depend on the seed? So is it?
No.
No, thanks. Right, because we can be close to the border, right? So for example, think of this f of x. Here are, again, 2 successful invocations, and you can truncate and see that one falls from the left of the border, one falls from the right of the border, and it's not the same value. So what you can do is use random shifts. So what Saks and Zhou do is they choose some zeta, shift the return value with high probability over the new randomness zeta. We're not close to a boundary, and now we can truncate. So with high probability over zeta, for most y's, we get a value that does not depend on y. And the value itself is epsilon prime close to f of x. Okay, so it's simple and powerful. Okay, and again, it enables them to eliminate dependencies between consecutive applications of Nissan's algorithm. Okay. So what's the Saks and Zhou's algorithm? Now we're ready to give an outline. So we pick a seed for Nissan and square root log n independent shifts. And for square root log n iterations, they take each shift to be O log n bits. And then we compute Nissan. We ask it to raise to the 2 to the square root log n power with some 1 over n squared accuracy. Shift and truncate, say to 1 over n accuracy, and repeat. It's a randomized algorithm, so to de-randomize it, we just average over all the h's and of the h and zetas. So to improve upon this algorithm, let's understand what's the bottlenecks, so what's the barriers. So the space complexity comprises two factors, or 3 factors, actually. The first one is the cost of the shifts. So we have square root log n shifts, each cost log n bits. This gives you already log to the 3/2 n. And this term is both the length of h, the seed for Nissan, and also the space it takes to compute Nissan at each iteration. Okay, so we have quite a lot of factors that gets us to log 3 over 2n, and we need to take care of them all, right? Okay, cool. The first bottleneck is the magnitude of each shift is 1 over poly n. And Saks and Zhou tells us, okay, let's use O log n bits for each shift. But it's not a real bottleneck. I mean, it's a bottleneck, but it's not hard to see that in contrast to the magnitude of each shift, which needs to have n in it, the amount of randomness doesn't. So it can be independent of n. And we use roughly log W random bits per shift. In other words, we use roughly 1 over W, we use roughly W shifts. So overall, this requires a seed length of square root log n times log W. Okay, so we already can clear one factor of the space complexity. Okay, but the more severe bottleneck is that the Nissan generator is costly if either of the following two things happen. If the matrix is represented using many bits of precision, or if we require high accuracy from Nissan's generator. So what do Saks and Zhou do? They work with 1 over poly n accuracy, already bad, and O log n bits of precision. Okay, so this gives us the other log 1.5 n factor in the space complexity. And the thing is, we do need this accuracy, because if you take a stochastic matrix which epsilon approximates some other, and you raise it both to the power of n, you do get a factor n blow up in the accuracy, unless you there are ways around it, but not in this general scenario. So we do need to maintain accuracy of 1 over n. So the question is, what do we do? And our strategy, which which might seem strange at first, is before we apply Nissan, we purposely decrease the precision of the input by truncating its entries to a precision of only 1/W. And recall that we're in the regime where W is much smaller than N. And also, when we apply Nissan generator iteratively, we only do it with accuracy, with a mild accuracy guarantee of 1/W. Okay. So what do I mean by truncating? We can actually incorporate it into our algorithm. So I just want to remind you, these are the standard Nissan parameters when we want to raise a to the power of r. And you see that we have a factor of s times log r, where s is the number of bits taken to represent the matrix. And I just want to say, what if we truncate to t bits of precision? Okay, of course, we have an additional error on top of epsilon, but the seed length, the length of h, becomes smaller. It's only t times log r, which will be the dominant factor. This will give us the log w times square root log n. So we're good in terms of parameters, but it shouldn't work, right? The accuracy is too bad. Okay, but just in terms of parameters, we're fine. So let's see if there is a way to keep the parameters intact, but improve the algorithm and its analysis. Okay. And as I said, I'll just say it again, that mild approximation is not enough. We need somehow to restore the high precision approximation of 1/n. This is 1/n exclamation mark, not 1/n factorial. Okay. So here enters Richardson iteration to the picture. And we view Richardson iteration as an error reduction procedure. So here's the statement. If we have the original A and R matrices, A1 up to AR, such that each AI mildly approximates A to the I. So note that it's crucial we get the original matrix and approximation to its powers. Then there exists a very simple space-efficient algorithm. I can show it to you offline. It's very simple. That takes all these bunch of matrices and outputs a much better approximation for the rth power. Okay, so it's like 2 to the minus k. And the space is doubly logarithmic in the accuracy. So if you want r times 2 to the minus k, you need space log k times log rw. Okay, so that's a great dependence. And let's see if we can incorporate it into our iterative scheme. And yeah, I just want to say a few words about the Richardson iteration first. Is that, as I said, it's very space efficient. And in our case, this the space complexity is only log w plus square root log n. Okay, so if you multiply it by square root log n, because this is the number of iterations we do, it will exactly match what we need. This log n plus square root log n log w. And Unfortunately, we cannot, in general, kickstart the process if we have a constant error. Say, know that I did need 1/r error in order to kickstart the process. There are some works in some very specific settings which do get something better, but in general, you do need 1/r. And you need access to the original A and to all its intermediate approximation of all its intermediate powers. Okay, so what do we suggest? After each mild Nissan invocation, let's retrieve the higher precision using the Richardson iteration. And although we decrease the precision before using Nissan, I'm not really losing it because we need to devise it in such a way that we'll still have access to the untruncated matrix. And always remember that we're at a space-bounded setting. So we never write down entire matrices. We only have very, very limited number of auxiliary bits. So this should be done space efficiently. Okay, so the Richardson iteration combines the untruncated matrix and mild approximation of its powers in order to get a high precision approximation of the rth power. Okay, so in just as a very high level outline, how does our algorithm look like? For powering first. So we start with our initial matrix A. We truncate it, okay, to decrease the number of bits that each entry has to log W bits. We apply Nissan, but with accuracy 1/W. And then note what we have. We have Nissan, but we also have our original A, so we can plug them both to our Richardson and get some R0. We use Richardson to accuracy say 1/n². We do shift and truncate because we still need to seemingly decouple the dependencies. And that's it. Truncate, Nissan, Richardson, shift and truncate. Okay, so we have the truncation to decrease error, and we have the shift and truncate to remove dependencies. Okay, and so on and so forth for square root log n times. So it has this alternating nature where we switch between mild approximation of 1/W and high precision approximation of 1/n. And the nice thing about it, which is pretty surprising, is that you can actually maintain 1/n accuracy without using log n space per iteration, which is kind of unique in this area of study. Okay, so before I move on, let's put it on the slide and let me know if it makes sense. Okay. Okay, so now we have different AIs. So a first thing to try is actually, well, do the same. Instead of approximating powers, just approximate products, like chop A1 up to AN, like do a tree structure. I have like a sketch in a slide. And just do the same thing. And seemingly, again, after square root log n iterations, the entire iterated product is approximated. So here, just do the same. You know, at first for powering, all these intermediate computations at each level were the same. Okay, but now they're distinct. Each node represents some Nissan invocation. So do Nissan, shift on Kate, and Richardson, and just do the same. So we will follow this tree structure, but there are quite a few issues. Let's just briefly discuss them. And the first one, which is the major one, I'll just mention them briefly, is working with the shifts. So remember that our algorithm for matrix powering, we invested log W bits per shift, and we had square root log n iterations, and it was fine. But at each level, right, at each level here, we had the same matrix. So it made sense to use the same shift. But now we have about n intermediate matrices. So we cannot afford independent shifts, and we cannot afford union bounding over all subsequences. So something needs to be done, something a bit radical. And the idea is, instead of shifting intermediate matrices, like instead of incorporating shifts within the algorithm, just forget it. Just shift the input matrices, and that's it. And use the same shift for all input matrices. So just shift the input. Sorry?
Just background noise. just go on.
I'm sorry, I didn't hear you. I didn't hear it.
I think it's just background noise. It's not a question.
Okay. Sorry. Okay, got it. Okay, so we shift once, and it's only like it's the best you can hope for. It's only log n bits overall. But the analysis is obviously more delicate, and we need to study what happens when we just shift the input. We need to keep track of the way the matrices and the error evolve. And actually, if you think about it for I don't know, for some time, you'll see that this can't work, but you need to do like a little bit extra, and we actually end up introducing a second Richardson iteration now for the purpose of handling dependencies rather than improving the accuracy. But let's not dwell on that, because as you'll soon see, there is an even more elegant solution. So this was the shifts problem, which was the major one. We have more minor things to overcome. For example, we need to improve Nissan's generator because we need to take the confidence parameter smaller than what we needed it to be in the matrix powering algorithm. And there's actually, if you didn't know about it and you're interested, it's actually nice to know there is to improve confidence parameters in PRG. We can use a sampler. It's called a sampler trick, and we now call it Harmoni's sampler tricks from the Harmoni's work, or also the Harmony Wigderson generator. But we employ it here. And we also need to do better space complexity analysis. But this is minor compared to the shifting. But I do want to tell you a different way of doing distinct AIs due to Louis Paterman and Ted Pine very recently. So based on our matrix powering algorithm, they handle the IMM case concurrently and independently using the following beautiful approach, very elegant. They proved that most applications of Nissan's algorithm will be good even without shifting. And they did, and they proved it by showing that Nissan's PRG can also fall related like an error indicator read-once branching program, which is a technique we often use. But there's still an error blow up, so they also need to keep using Richardson iteration. So the nice thing is the observation that multiple shifts are too expensive for IMM if you want to beat Saks and Zhou. We solved it by doing one initial shift and error reduction. And they said, well, you don't need any shifts. You just do error reduction. Okay, so questions up until here? Where am I on time? Okay, still have 5 minutes. That's good. Okay, so just to complete the picture, there is the black box challenge, which I haven't discussed, and just want to put it on the table and saying it's still a challenge. So the challenge is to construct PRGs for read-once branching programs, which is the non-uniform model that corresponds to space-bounded computation. And I won't even define, yeah, and just of course, I mean, if you know it, then you know that PRGs for length and with W is what we need to approximate IMM. But I'll just give what a PRG is by saying which algorithm does it induce for IMM. So here is a way, a very bad way, to compute IMM exactly. Okay, this is a terrible way to compute IMM exactly. This is not how you would do it. But if you only wanted to approximate IMM, the pseudo-randomness challenge, the black box challenge, asks you to construct a sparsification of W to the n-1. So come up with this set curly D, a subset of all the walks that you see here. 1D should work for all the AIs, all the stochastic matrices. And this is exactly how you should do the approximation algorithm. Okay, this is the black box challenge for IMM. And what's the quantity we're after? How much does it cost in terms of space? Assuming we can generate D efficiently, this is just log the size of D. This is the quantity we're after. And as I told you before, when W is constant and we're only looking for any algorithm, then it's easy. You can just do iterated powering. But if you want a PRG, like this specific algorithm, then only recently we know how to do it for W equals 3. This is due to Mecha-Reingold and Tal. And for W equals 4, we have nothing better than Nissan. Okay, so recall that state-of-the-art PRGs fall short compared to algorithms. Now, of course, you might say, okay, but I'm interested in algorithms. But historically, even if you're only interested in algorithms, PRGs often help. And so one open problem is make this text show based constructions fully black box. There are a few ways to interpret this sentence, but in general, and you can feed it back and have direct applications for BPL. And I'll just mention that the Paterman-Pine paper show that for medium Ws, you can get a Saks Zhou type result even without shifts and without error reduction. So essentially, the only non-black box component is some canonicalization step in instance generator, in instance algorithm, which I haven't explicitly said what it is, but it's, even if you kind of forget about the shifts and forget about the error reduction, it's still not black box. So one concrete open problem from this talk is this. Okay, so yeah, thanks for listening.
Well, thank you so much. Questions for me?
Yeah. So is it easy to describe this Richardson iteration, like you said?
Yeah, sure. If you just want the algorithm, I can give it to you in a minute. I'm not sure. Do you want to?
Sure, yeah, that seems like magical.
Yeah. But okay, so let me show it to you, and then do I have like a couple of minutes, or do you want to do it off? I mean, okay, so let me share again. Yeah, so I'll show you Richardson for oh sorry. Let's unhide. Okay, so I'll show you how to do Richardson iteration for reducing the errors in matrix powering. So say you take some stochastic matrix A. And I know I minus A is not invertible, but forget about it. Let's assume that it is. And just, you know, it doesn't even matter. So you see, put the matrix A, embed it in the off diagonal. Okay, so here we have this path tensor with A. Okay? And it's not hard to see that if you take the inverse of I minus this, you get on the left, on the bottom leftmost place, you have like the largest power. Okay? Now, of course, we don't have that, right? We want to approximate it. We want to start from a mild approximation, say epsilon 0, and get an approximation, say epsilon 0 to the power of k. It's a very simple thing. So here you see LK, right? And what's the algorithm? Just do the sum, where L is the original matrix where, so L is just I minus this. So it's I on the diagonal and minus A on the off diagonal. And L inverse tilde is just, you replace each true powering with an approximation of the powering. So if you see the top matrix, just replace each true power with the approximation of the power and compute this, this sum. And like if I had 15 more minutes, I will be able to prove it and also kind of show you how it's actually gradient descent. And you can actually also have an example. No, sorry, but yeah. So here is what I said, that you replace the true powers with the approximations. So so yeah, it's just basically a degree k polynomial in the approximations and in the true matrix. This is just it. It's a low degree polynomial of degree k, and the input to this polynomial is your mild approximations and the original matrix. That's it. It's a degree k, very explicit degree k polynomial.
Cool, thanks.
What is the scale Hamilton algorithm that you mentioned? That
you're.
I don't know. I saw the title.
Yeah,
there.
sure. No, it's in Hebrew we say achinoti mirosh. Okay, I came prepared. Let me share again. So this is for computing powering exactly. So you compute a characteristic polynomial, which takes log square W space. You compute xn mod px as a polynomial, and then just compute this polynomial, just evaluate a on this polynomial. And you can just, it's polynomial division, as you can see, and then by Kiley Hamilton, this is a of n. Yeah, I don't think it was that well known, but as you see, it's very straightforward.
Thanks. More questions? That's all. Let's take the begin.